Hey there, so in this video I'm going to cover quite a few things. I've been playing around with electronics. I've also been spending a lot of time with retro computers. I've been building out my collection with Commodore 64s, BBC Micros, Amiga 500s, Macintosh SE, and now I have an MSX computer on the way. And so I've been playing around with a lot of stuff, and one of the things I've been also doing is building a 6502 computer based off of Ben Eater's videos and the kit that he sells on his site. And one of the parts that came with the kit was faulty, and so I had to wait on that part, and then I started another project while I was waiting on it to arrive, which I'll dive into in this video. So what I'm going to show you today is I took his EEPROM, Ben Eater's EEPROM programmer that he's got on GitHub, and I made some changes to it to allow writing to multiple ROMs, to get some output to it, to make it a little bit faster, to deal with the software data protection, and basically, kind of played around with that. Probably not perfect, but the point wasn't perfection. It was basically just to learn how to do electronic stuff. That's a brand new hobby of mine. I've used retro computers since I was retro, a little kid, but actually playing with the hardware and electronics is actually relatively new to me. So I'm going to show you some changes I made to the EEPROM programmer. But I also love my Commodore 64, and I like programming on it. And so as I'm doing the videos and we're using Python to write the opcode, the assembly code for the 6502 computer, I'm like, what would be more fun is actually writing this on a real assembler on the Commodore 64. And so I'm going to show you using Turbo Macro Pro to write assembly code, which then gets assembled to disk, which then I send from the Commodore 64 over to RS-232 to the EEPROM programmer to actually write the bytes to the EEPROM. Which is a lot of fun. So I'm going to show you all of that. I'm going to show you receiving it on the Arduino. I'm going to show you a little bit how I make sure that the data doesn't get corrupted along the way. Actually, I'm going to show you that the data did get corrupted along the way for me for a few reasons, which you'll see in the video. Then I'll show the actual writing of bytes to the EEPROM and show that the whole thing actually works. So anyway, I hope you enjoy this video. I've learned a lot from the community, and I'll put thank yous in the comments down below the video. I hope this is helpful to some folks, and I hope you join me and make this thing better, because I actually think it's a very fun project and a fun thing to do. So why did I do this, and why might you want to do this? Well, first of all, it's fun. This is, like I mentioned before, it's combining a bunch of hobbies of mine, also a good way for me to learn. But there are a couple advantages actually to doing things this way. First of all, you get to use an assembler, which is fun in and of itself. It's a little more fun, I think, than looking up the actual direct machine code stuff. You can actually use commands like load accumulator rather than looking at the actual code for load accumulator. So it's a little more easier, I think, to do the programming on it. I mean, there's a reason assemblers exist. But also, there is an advantage to this, that if you want to update a single address, a single byte on the EEPROM, and then you can use this way to do it. I know the existing tutorials that I've seen, basically you fill up the entire byte array and write the entire byte array to the ROM. This allows you to say, I want to write this specific data to this specific address or range of addresses, which you'll see in the video. So that is an advantage. Why might you not want to do this? Well, it is slow. I mean, all the communication is happening over 1200 baud via the user port. I think you could go up to 2400, but I just didn't. I've heard when you go those speeds, you might actually get data corrupted and that kind of thing. So 1200 baud, so it's kind of slow. If you were to write the full 32K, you might run into issues of timing, that kind of thing. And there's lots of moving parts. So if you could see my desk, which I'm not going to show you, it's piled full of things. So to get it to work, I have to hook up the EEPROM programmer to a power bank, got the C64 going, got it all wired together. There's just a lot of moving parts versus, just getting like one of these and writing to it. But that's no fun, is it? It's much more fun to do it yourself. Okay, so let's talk about the hardware. You may notice this looks pretty familiar, so I started off with the Ben Eater design on this, but I wanted to make some changes to it, mostly to learn because I'm new to electronics and I've never done anything like this, but also when I received the 6502 kit, this chip here, which was not actually this chip, it was another one, had a fault in it. So no matter what I tried, I would write to the chip, and there was a certain memory location that it had an error on every time. And this was with the programmer that I bought, also not just the one that I built. And so I was playing with the smaller chip while I was waiting on getting a new one, and then I thought, you know what? Why don't I just build it so that I can read off of both chips? And I can select between the two. So you can't see the screen right now, but it says upper EEPROM 28 pin selected. And basically, I built this little SR latch over here to switch between the two. And you'll notice when I switch to the lower pin, that LED lights up. And on the screen over here, it says now lower EEPROM 24 pin. And so I basically have wired up the chip enable out of the SR latch into each of the chips. So when you switch between the two, it actually enables one chip and disables the other. And I'm also feeding the output of that back into the Nano so that I can read that status and then display on the screen which is selected. Is there a reason for that? Not really. It was just kind of fun to do, and I wanted to be able to see it in action. So I added those. I also put it on two breadboards, and these breadboards I didn't realize you had to get power both to the top, bottom, left, and right. So there's a whole bunch of power stuff. It's all kind of a Frankenstein thing, you can see. I also wanted to be able to have this small OLED screen, and so basically anytime I print to the serial output in the Arduino, I'm also printing to this device. So I basically can use it to kind of log what's going on, which you'll see when I run the program later. What else did I do that's different on this thing? I think that's about it. I am using the analog pins to run to these. What you can also see hardware-wise, you see some heading to the power bank. So once I put all this in place, the Nano didn't have enough juice basically to power the whole thing, and so I'm running it from my bench power supply. And I'm also wired it into my C64. So I bought this user port breakout board, which is super handy. You can also just get a connector and wire up the connector, but I like this because I can play around a lot with it, and I'll get into the exact wiring in a bit. But as you can see, I'm going from my board, from the C64 over to the board. Basically, well, I'll just get into it now. Okay, so let's talk a bit about how I wired up the C64 user port so that I can communicate via RS-232 over to the Arduino serial. So you can actually use the TX and RX ports, but then you can't use them to communicate with the computer, and I wanted to be able to do that as well through the USB. And so instead, I wired it up. I found this link on Retro Game Coders, which I'll provide a link in the video to. But basically, you connect A and N coming out of the user port to ground. You connect B and C, B and C or RX on the C64, which connects to the TX on the Arduino. And M is the TX on the C64 that connects to the Arduino's RX. And by RX and TX on the Arduino, they suggested pins 10 and 11. However, those pins were already in use for me on the EEPROM programmer, and so I use ports A0 and A3. Now, you can actually use analog ports as digital ports. There's a couple of caveats in there, but it works. It totally works, and so that's what I did. Okay, so what did I actually want to do with the Commodore 64? So I wanted to be able to write the assembly code that I would be using to program my EEPROMs in an actual assembly assembler, basically. And so I'm using Turbo Macro Pro for this, mostly because it has a feature of being able to assemble directly to disk. And so what I do, the workflow is I write some code in Turbo Macro Pro. So launch that really quick. Okay, so I do something like, well, first I got to start by giving it a location. So let's say we were going to write to our EEPROM uh, at 0. Like that's where I'm mostly going to write things is to 0. And then I maybe want to say, load accumulator with the value of, and then maybe I want to store that accumulator in some memory location like I don't know, 1,000, let's say. Then I'm gonna do some no ops, just right. Okay, and actually I'm gonna switch my Pi 1541 over to a actual disk, storing all of this stuff. And so let's say I would then want to save this file. I can save it out to temp s for source. Okay. So that's going to save the actual source for this. Uh, and then I can actually assemble this directly to disk by hitting arrow, which I'm sure has a name, and 5. And then I give that a name, we'll call that temp O. And so what that's actually going to do, you'll see, is it's actually assembling the code to location 000 through 0007, and it's storing that to disk. So you wouldn't want to actually assemble this directly into memory at location 0. I'm sure that would be very bad, but it assembles it to disk, which is very handy. Okay, so I actually have a couple of programs I want to show that very, very small ones that is actually directly from the tutorial from Ben Eater on building the 6502 computer. I'm kind of early in that process, but you'll see what I want to do with it. So first of all, I'm going to load one that I call reset address source. And you're going to see this is very simple. And this is just going to write some bytes, just going to write bytes to a location in memory, which is really the start location where the CPU is going to get its first instruction from. And I'm not going to dive into all the details on how this works or why it's 8000 on a 32K chip. Follow along all of Ben Eater's tutorials for that. But one of the things that's actually really handy about doing this on the C64 instead of like a Python script or something is I can actually write to very specific memory locations as little data as I actually need to. Okay, and so I've already assembled this previously to disk, but I'm gonna just do it again. So this time I'm gonna name it with the at colon, so it'll overwrite the file. And I'm gonna call this for reset address O file. Okay, so now it's assembling it to disk. You can see the start location is going to be 7FFC, and it's going to just go through 7FFD because it's basically just writing 2 bytes to that memory location. Okay, and then I have another kind of test, which is another part from the Ben Eater story. He's using the value 42, so I'm going to do the same. I'm going to load that file that I've already written prior to now. And all this is doing is at memory location 0, so this is the start of the ROM that we're writing. It's going to load the accumulator with the value 42 hex, and then it's going to store that in memory location 6000, and then I just added a bunch of no ops into. Okay, and so I could assemble this to disk, call it 420, which is like 420, not a joke. But well, actually, I'll just do that again. So this 5, and I'm going to call that 4. Okay, so now it's assembling, and now I've got 2 files that are written to disk that are assembled code. And so now if I go back to basic and I load my disk, see those 2 files see 4 files, the source. So you can see 42S, 420, that's a source file and object file, and you see reset address S and reset address O, which are the 2 files that I'm actually going to be sending or writing to the EEPROM. The other big file that I wrote is the actual code that sends the file through the user port via RS-232 to the Arduino, which then writes it to the EEPROM and then gives status back. So I'm going to actually walk through that code actually right now. And so I'm going to load, I called it send bytes. I'm just going to load this code. Okay, so I'm going to just list like the first couple good lines, and you'll see I'll just kind of walk through it step by step. Okay, so one of the things you note, line 40 here, is opening, this is actually opening the port via the user port to do the RS-232 communication. And so logical file number 2, 2 I think means modem. By the way, I'm new to a lot of this stuff, so I'm not going to probably speak to this 100% correctly. People can correct me in the comments if you want. But this is telling it actually, the char 8 is telling it to run it to do it, communicate at 1200 baud. So that's as fast as I wanted to do it. Apparently you can go up to 2400, but it's unreliable. And for writing an EEPROM, I didn't want it to be unreliable. And then the char 0, I think basically says to do handshake mode. This is all documented in the Commodore 64 user's guide, which I highly recommend. It's towards the back of that. It's super helpful. And then you have to basically do a get to kind of get data flowing, basically. Okay, and one note that I discovered is you actually have to open this at the very beginning before you do anything else with any variables, because one of the things I noticed is that once you open this, it like wipes away all variables that you have in your basic program. Like all the integers I had were reset to 0. So don't know why they did that. Must have wanted it to be super clean, but nevertheless, I found out through quite a bit of actually debugging that that's what you needed to do. Okay, and then I open the command channel to the disk because I want to be able to see actually when I open the file that I'm going to send if there's any errors in opening that. Ask the user to enter a file name. By default, it just uses an example file that I have on, and then basically prints out the file that we're going to use. And so now I'm going to list, let's say, okay, actually, list 300 to 500. There we go. Just declaring some variables. So basically the data that I send is of the form, I have a message header, which includes the type of message that we're sending and the number of bytes that we're going to send, which is a max of 8 for each chunk that I'm sending. I'll get into the reasons for that, but simplicity, you could do more. But basically I send a message type, a checksum with, sorry, a header includes a message type and the number of bytes that we're going to read. Message type 1 is basically we're starting to send something new. Message type 2 is we're continuing to send data. And then after I send that header, I send a checksum, and there's 2 bytes to that, an upper byte and a lower byte, and I'll get into how the checksum works in a bit, but I basically wanted to make sure that when I send the data that it's not corrupted over the wire. And actually I found out like it's super noisy, so I built this you'll be able to see it, but I built this little AV breakout board here, and it's like super noisy. But anyway, I built that so I can get S-video out. But I noticed when that video cable is crossing over any of the data lines, they get corrupted. So the checksum actually is super helpful. So basically, that's that. And now if I list 500, 700, I actually open up the file that we're going to send. Now Turbo Macro Pro assembles the files as PRG files, which was kind of a surprise to me, but it does. And the first 2 bytes of that file are the address, and the rest of the bytes are the actual bytecode. And so that's super handy because as you saw when I assembled the 2 programs earlier, one of them I'm going to use to actually send the start location for the start instruction for the processor, and then the other file I'm going to send is going to be the actual bytes starting at 0 in the ROM. And so the fact that the PRG contains that location in the first 2 bytes is actually super helpful. So basically, yeah, so then line 520 there, I'll get to the error checking in a bit, but I basically just open the disk and see if I open the error channel on the disk and see if there are any errors, and so on 530. If there are any, then I jump to the end and clean things up and exit. If there's not, then I get a byte. So get number 5 is reading from that file that I opened. Reads a byte in basically, and then I grab the status at that moment. The status is going to be set to 64 if we're at the end of the file, and so I use that later. Line 570 was some trial and error. So if the byte that we read is 0, then that causes all kinds of chaos when you try to actually send that across. And so I set it actually to a null character, char 0. I think that's what's happening. That's what it required to get the data to actually flow appropriately. A 0 byte from the file. And then I store that byte in a byte array that has a max of 8 bytes in it, increment that, and then basically CS is the sum. So as I'm going, I'm summing up basically all of the bytes, and I'll get to the checksum algorithm in a minute, but that's where I start. And then if we've now read more than the max number of bytes, then I send the data. If not, I keep going until I hit the end of file, which is at EO not equal to 64. if it's not equal to 64 and then I just keep basically reading. I actually do a little cleanup after I send the bytes. You'll see that in a minute. So now I'm going to go to 1,000 to show you the actual sending of bytes. So list 1,000, 100. Okay, so here's where I actually send the data. So first I do the line 1010 go sub 3000. That's going to do the checksumming. So I'll show you that in a minute. But basically I go calculate the checksum first. And then this is the message header, as I mentioned. So the first 3 bits of that byte are the message type, either a 1 or a 2, and then the rest of it is the number of bytes that I'm sending, which is always going to be somewhere between 1 and 8, basically. To actually send the data, you just print. So print to the logical file number that you opened earlier. So in line 1050, you can see that I'm printing the message header. And then in line 1090, I'm printing the lower byte of the checksum that I calculate. In line 1110, I'm printing the upper byte of the checksum that I created. And then I actually send the byte array. So I iterate through the array. Line 1130 is just a progress indicator. Line 1140 sends the actual byte. And then I just iterate through them. Basically. And then line 1170 is actually waiting until all of the bytes have been put in the buffer before continuing. And then there's some cleanup. So let's say this is a cleanup. So I'm just resetting all the values there. Okay, so now I want to show you the checksum algorithm here. Okay, so I thought it might be helpful to actually walk through the checksum algorithm on both the sender side and the receiver side to show how we make sure that the bytes that we send across are actually the bytes that we expected to send. Now, one thing I want to point out is I only do this for the actual data, not for the header, and I realized as I was debugging some issues that I should actually do something similar to the header. I just haven't done it yet. But anyway, the algorithm's pretty simple, and many of you may already know it, but I just thought it'd be worth walking through. So let's say you have these 4 bytes that you want to send, 234, 123, 95, and 33. On the sender side, the first thing you do is you sum up all of those bytes, which sum out to 485. And the ones complement is actually the inverse of the bits of the number in binary. So let's say 485 in binary is this, 0001, 110, 0101. And then I'm going to actually use an XOR on that number to get the inverse of it. Commodore 64 does not have an XOR function in BASIC. You can do it in the assembler, but not in BASIC. So that's why you see the kind of weird code for that. But basically what I do to do the ones complement, and this only works up to 12 bits in the way I implemented it. Could do better. But basically you get 2 to the 12th, 4096, and subtract 1 to get 4095. So that's these 12 bits all ones, and then you XOR that with the 485 in binary, and you'll see what that effectively does is flip the bits from the original number. So this 0 becomes a 1, this 0 becomes a 1, this 0 becomes 1, this 1 0, and so on. And then you actually sum up this resulting number, which is 3,610, and that's actually what I send over wire as the checksum value. And on the receiver side, what you do is you add the bytes that you receive. So it should be 485, because if you sum up all the bytes, you get the same as you got on before. And then you add the ones complement number that we sent to the bytes that you received. So remember 3610 was the sum there of the ones complement. And so I add 485 to 3610 and I get 4095, and then I make sure that all the bits and the number that we got are 1. And so 4095, as you remember before, is all 1. So it's not a perfect algorithm. So like if these bytes arrived in a different order, if we got 123 then 234, you'd see you still get the same value, and it would assume that the data that you sent is incorrect. Also, it is theoretically possible that you could get bad data and the bad sum also, but theoretically the idea is if any of the bits or any of the bytes get corrupted along the way, so instead these sum up to 473, and then you add 3610 to 473, you're not going to get all ones because you're not going to get 4095. Or let's say the checksum that you sent, or the ones complement that you got was 3500. 485 plus 3500 is not going to give you all ones when you check the bit. So that's the basic algorithm. It's relatively simple, not super expensive, I don't think, to implement. I think the C64 has some like parity checking or something, but I just went this route because I wanted, and it was relatively straightforward. And then 3080 on. I just exit cleanly. I just close everything, and then 59980 was reading the error channel that I mentioned earlier. So it's just reading from the disk. In my case, it's Pi 15.1. And then if there's errors, then it sets the error thing. Continues. So that's it for the program. I kind of walked through it quickly, and that was my first practice at it. So if you have any more questions about it, I can answer it in the comments. I'll also add this code to GitHub so that you see it for yourself. Okay, so I want to walk you through the Arduino code. I'm going to kind of zoom through this a little bit because I think there's probably a lot more better examples out there. Also, this is really bad code. I mean, like really bad code. Brand new to Arduino and brand new to electronics, so please forgive me for that. But anyway, so most of this is going to look pretty familiar. You can see earlier I showed you that I've wired up the chip enable coming out of the SR latch to switch between the two EEPROMs to pin 13. And so I use that to basically read which EEPROM is selected. Also want to mention, so there's a couple things I do in this code that I've seen some people on Reddit struggle a little bit with, or at least have some challenges on. I also want to give a thank you out. There's a great tutorial which I'll link to on disabling the software data protection on some of the EEPROM chips you get. I had that issue on my EEPROMs, and so that was super helpful. I did things a little bit differently than that example out there, but not a lot different, and so that was super helpful. And so in this code, I'm actually going to be disabling software data protection if it's enabled on the EEPROM. So I'll show you how I do that. Also show you the code for the screen on there, and then I'll show you the communication between the Commodore 64 and you know. Okay, so in here you can see how I wire, which pins are wired up for devices, for the Commodore and for screen. And then just basic screen stuff. I'm using the SSD 1306 ASCII library to do the screen communication. Um, I'm using I2C. It's an I2C device at address 3C for that. I'm also using software serial. As I mentioned earlier, I'm using pins A0 and A3 to communicate with the Commodore 64. And because I'm not using the built-in TX and RX, I'm using the software serial library. I keep track of the last address that I wrote, so I'm not constantly setting addresses. This is for performance, as was also mentioned in the sample code for that I'm going to link to, because basically the default code out there in BinEater's repo, basically every time you read or write, it sets the address again, which loads the shift registers and does all of that stuff that's kind of unnecessary, and so I keep track of that address. I also keep track of the start address just for printing out, so when I receive data from the Commodore, uh, I get told which address that I'm going to write that data to on the EEPROM, and I'm basically storing that and then outputting at the end of all the writes, where did we start and where was the last address that we wrote to. Just declared some strings, probably a better way to do that, and then just some status kind of information. I'm sure there's better ways than using global variables for all of this stuff, but maybe not. So I have a buffer where I keep all the bytes that I receive from the Commodore, and then a buffer to keep the header information. I'm not going to go through all this stuff that's in BinEaters or other tutorials, just the unique stuff. Here's the enable SDP code. So basically, I set the data pins to write, and then you write this specific data to these specific addresses. and it'll basically, this will enable SDP and this will disable it. I did a little bit of testing. It wasn't perfect, so there's probably a better way to do this, but it worked pretty consistently and it fixed my chips. And so basically, before I do any writes, I disable SDP via this code here. Um, yeah. I'm gonna skip over. Oh yeah, I want to talk a bit about this. Okay, so this is the writing data to the EEPROM, and this is something that I haven't seen anybody else do that I think actually makes this quite a bit faster uh, to write than Ben Eater's program or any of the ones that I've seen out there, because in his, basically when he did a write, he had multiple sleeps in the code to wait for that data to finish getting written before doing anything else or before reading it back. But I read the data sheet and I saw that actually once you do the first write, um, it will change the value of that, of coming off of that address to the ones complement of the data that you wrote. And so basically when I write, I have this validate data function, and I'm sure there's something wrong with this, so somebody tell me in the comments if there is. But basically I set the data pins back to read, and I poll until they equal the value that I wrote to them. And so let's say I'm writing to address 0 and I wrote the value FF to it. Okay, so in this here, I'm doing the digital write to write the FF and then pulsing it to trigger the write. And then I'm calling this validate data function. And basically I delay just a little bit. I think that's a millisecond. You could probably shorten it even. And then I read back the pin at that address that I wrote to. Um, and then figure out how much time has elapsed. And if the data doesn't equal what I expect it to equal, then I just keep looping until I time out. And I have a timeout of 500 milliseconds. But basically, usually within like 3 or 4 milliseconds, it's actually finished, and I don't actually have to sleep. And so I basically can use this polling mechanism to make it as fast as possible, as opposed to a sleep of unknown time. And so I think that works better than a lot of what I've seen out there, and so I'll share this code. But it seemed to work really reliably for me. I don't know if that was unique to my um, ROMs, or if that's true of any of them out there, that they have that they work that way. But that worked really well. And then I have a bunch of print stuff. This is the printout, so I'm basically anything that I receive back, I'm printing to the serial monitor, but I'm also printing it to the screen on the device itself. I won't go through any of that stuff. Basically set up the, I have a lowercase r there, lovely. Set up the pins for the RX and TX with the C64. Again, I've got that at A0 and A3. Ignore this write test data, ignore this, ignore this, ignore this. This is just where I print out the bytes that I've received. Okay, I wanted to get down to a couple of things. Let me go down to setup. Okay, setup. So basically, a lot of this will look familiar if you've done the bin eater thing. The one thing that's different is, as I mentioned, I am checking the chip enable. I'm setting it up as an input. Also, I can't remember if this was in the original design or not, or this is something I did, but I'm controlling the write enable and the output enable via the controller. I think Ben Eater wired one of them to ground. I don't recall correctly, but I'm actually setting them via the Arduino. Then I initialize the screen. Reset pipe is just cleaning up some variables that I have to use for the communication with the C64. Yeah, as I just mentioned. So I just keep track of when I last received data. So there's a timeout. So if, for example, I was expecting 8 bytes and I only got 7 and something happened on the C64 end, after a certain amount of time, I'll just reset everything basically and then start expecting new data again. And so in the loop, I'm just checking which EEPROM is selected and updating the screen if it changes. Again, I'm setting to see if I've timed out and then kind of cleaning things up. And then here's where I actually receive the data from the Commodore 64. And so from that software serial, I do a read. basically I was printing out. This should be commented out. Print out the byte that I received. And then this is where I do some decoding. Okay, so I keep track this current header byte is just a status variable. As I get a new byte, I'm working my way through each of those bytes in the header, and then I start reading data. And so that gets reset to 0. So the first byte that I receive, I expect to be a header that contains, again, the type of the message that I'm receiving and the number of bytes to read, and then I receive the low byte of the checksum and then the high byte of the checksum, and then I start receiving all the bytes from the actual data that I want to receive. Okay, so it's very simple. That's all it does. It's quite easy to do the communication over the software serial over RS-232 from the Commodore side. And basically, when I actually process the receive bytes, I wanted to show the checksums thing in a moment, but this is where I read the address. So again, the address is sent in 2 separate bytes, with the low byte first and the high byte second. And then I just start reading data basically down here. And so I set the current address. So the first 2 bytes are the address. So I set the current address in the EEPROM to the first 2 bytes that I receive. And then for the data that I receive, each time I read a new byte, I update the address and send the data to that new address. Basically, and then if there's any errors or anything, I indicate that and I stop working in that case. Okay, so I want to show you the actual writing of the EEPROM. So first, I actually have a professional, what's it called again? TL866 2+ EEPROM reader, and so I'm going to use that in MiniPro to basically write all FFs to the EEPROM to start with, so you can see it actually working. And so I've got a Python script that I will show you. Cat. Okay, so it's basically just going to write all FFs to entire ROM, and so Python make ROM, get a file called .bin. So if I hex dump, see it's all FFs, and so now I'm going to actually program that to the okay, that's okay. So I'm going to write the digit bin. Okay, and now I'm back out that ROM. We'll call it out stump. Okay, so you can see the ROM actually contains all Fs right now. Okay, I have put the chip back in the EEPROM reader. Now I'm going to power up. Okay, as you can see, this isn't connected. Set. Okay, so as you can see, the chip is in, nothing's connected on the Arduino, and I've got the LCD is showing that it's awaiting data. And so now I'm going to run the program, and it asks for a file name. And in this case, I'm going to first do that reset address object file. I'm going to send that. And as you can see, it reads it and sends it over. And I don't think you can see on the little screen here. Let's see if I can hold it up closer, if it can actually, yeah, it maybe not, but it shows that, oh, and actually it shows error writing EEPROM. So error. Okay, so I've been fiddling with it, trying to figure out why earlier I was getting an error, and I realized I was not calling the SDP disable SDP function. So, and this is a different ROM chip than I was using earlier, so I was trying a new one, so I think that's what was going on. However, then I started playing with it again and I was getting some more errors, and so it seems a little bit flaky at the moment, which it wasn't before, so I don't know if there's any noise or something going on. Okay, so videos never quite go as anticipated, so as I showed before, I was having some issues reading or writing the ROMs that I thought was related to forgetting to disable the software data protection, which may still have been an issue, but wasn't the one that I was seeing. Uh, and then so I pulled the ROM out and I realized a lot of the data that I had written was not actually correct, which was disappointing, but was actually nice because my error checking worked, so it showed that there were errors writing. However, I realized that something was causing the data to not be written. So I thought maybe it was noise with all the stuff that I've got going on over there, all of the wires crossing and custom made cables and all that kind of crap. Uh, However, when I went to pull the ROM out and read it with my reader, actually when I pulled it back out of my reader, I realized that some of the pins were bent. So it was late at night when I was recording and I was pulling that ROM in and out of my EEPROM programmer, and I realized that I actually bent some of the pins on the 256K chip. So apparently having bent chips that aren't connected can actually cause issues. So now I'm going to try it again, and let's hope that this actually works this time. So load it, my send bytes program. I'm going to run it, and now I'm going to send the first instruction for the CPU. See if it works. Okay, it does look like it worked. So it wrote to address 7FFC, and the data it wrote was 0080. So thank goodness, seems to be working reliably now. Now I'm going to run it again and send the actual program, which I name 420, which is 42, and an object file. Now I'm going to send that. That worked, I think. Now I'm going to actually switch over and I'm going to read the EEPROM and make sure that it actually correctly. And this time I'm going to use my actual like chip puller to pull this instead of my fat fingers. Let's get that chip pulled out of there a little more cleanly this time. See any bent pins this time, so it works. Okay, so now I'm gonna read the ROM that I just wrote. As you can see, this was what I did before I just wrote. I wrote all F's to it, so hopefully I don't have all F's anymore this time. So I'm gonna read the ROM out to this file called rom.bin.out. And now I'm gonna text dump of that file. I should see, hopefully, if I want to see. Okay, so this looks good. So 7FFC, which is over here, which is the start address for the processor, 0080, so that's great. And then if you look at Ben Eater's program, I believe this is exactly what we were trying to write. A942-8D0060, and then I wrote a bunch of no ops in. That is great. All right, so I actually wrote what I intended to write, which is a good thing. So note to self, do not bin pins on your ICs. Apparently that makes it not work very well. And I didn't record a conclusion, but that's the end. Thanks for watching.